Hi everyone. So we are going to pick up where our lesson left off. This is 2.4 and 2.5 for Algebra 2, and we're going to get into exponential modeling here. So just to remind you, the whole concept of modeling, mathematical modeling, is coming up with an equation to represent a real life situation. And that situation may be given to you, in words, or maybe given to you in data. There's lots of different ways that you can be presented with information and be asked to write a model. And a model is really just an equation that somehow represents that situation. Before we move on, I do want to spend some time kind of comparing the exponential models and the linear models. And really, this is also a comparison of exponential functions and linear functions, okay? Like we just said, exponential model is always based on repeated multiplication. So any sort of real life situation where you're taking a value and multiplying it by some value consistently, I'm multiplying by 2 over and over again, or multiplying by 1.5, or multiplying by 0.3, that's going to give you an exponential model. Linear models are based on repeated addition. And just so you know, anytime you hear the words constant growth, that's a linear model because that implies addition. Exponential models would just be called exponential growth. Okay, but constant growth is always referring to linear models. Okay, exponential models grow slow at first. Then they grow very quickly. So any sort of situation that involves exponential growth is going to move very quickly eventually, whereas linear growth is constant, grows at the same rate the whole time. And that's why we get that concept of slope when we're talking about linear modeling, because slope is that constant rate of change. I'm going to put rate of change here. So just to remind you, an exponential function is always going to take a shape that looks something like this, whereas a linear function is just going to look like this. And so what will happen is if I were to put these two kind of on top of each other, at first that linear model is going to show up, slightly higher than that exponential model, but there will always come a time when that exponential model takes off and just leaves that linear model in the dust. Okay, so just keep that in mind. That's a big concept on the SAT, is knowing the difference. If you look at a situation, knowing the difference between whether it's exponential or linear. Okay, exponential models also, I should probably throw in here, have that form a times b to the x. And notice the x is up in the exponent here. That's what makes it exponential. Linear models are that mx plus b form that you're used to. Okay, so let's move on to doing some actual exponential modeling here. And you'll notice this first question is given to us in terms of data. Let me just point out, back at the beginning of this lesson in the other video, we did this example 1. Technically, what we were doing here is exponential modeling. When we wrote this equation, this is an exponential model to represent this situation. So you can do modeling with word problems like this in real life situations, or you can do exponential modeling with data, and that's what we're dealing with here. Okay, this is going to be very similar to doing linear regression, except we don't want a linear model, we want an exponential model. There's really just going to be one button push that's a little bit different. So I'm going to try to very quickly, and I'm sorry, I should have had this in here for you already, but I'm going to try to very quickly put this data in here. Let me move this so you can see it, hopefully. Clear my lists, clear my lists. If I go too quickly for you, you are welcome to pause the video because I do recommend you doing this along with me and making sure you get the same values I do. So again, to get to this screen, I hit Stat and Edit. And what I'm going to do over here, because these are all given to me, I believe, in millions. Well, I guess these first few are thousands, but I think that's what I'll do because they all have 3 zeros at the end. So I'm going to look just at how many thousands it is that we're talking about. That just saves me some button pushing. It saves me from having to type those 3 zeros on the end of all of these numbers. It makes the numbers that are going to go in my model a little easier to work with, and I can just know when my answers come out that I need to add those 3 zeros at the end. So I'm going to type this in as 640, 990, 1,255. I'm just taking kind of up to those 3 zeros. Okay, and that process you should be familiar with from when we did linear regression, getting the data into your calculator. Now we're going to go back to Stat and over to Calc. Now, if we were doing linear modeling, we would choose this one right here. The only thing we're going to do differently this time is we're going to choose exponential modeling, which I don't remember which number it is, but it's pretty far down here. There it is. So exponential regression is right here, number 0. So I'm going to choose that one. On my calculator, I'm just going to hit enter at this point. On your calculator, you may have to scroll down to where it says calculate. And you'll notice that it gives me this a times b to the power of x. Now, this a value is kind of funky here. Gosh, this is so close to 0. It's not quite 0, but this would be like 1.17 times 10 to the negative 14th power, which means that I should really move my decimal point over 14 times. I really don't want to write out all those zeros, so I'm going to write my model still just using that scientific notation number. So I'm going to write it like this. 1.177, I'm rounding that, times 10 to the negative 14th power. Okay, and then my b value, it gives me as 1. Oh gosh, those 9s are screwing me up. I would probably normally go to 3 decimal places here, but I'm going to have to go 1.020 because of the way that thing's going to round. And then I would just go to the power of x. Okay, so here's a, b to the power of x. So here's why this is a little bit strange. This would be representative of like year 0. If we're in 1950, if we were to turn the clock all the way back to like year 0, this would represent what the population would have been under this model in that year. Now, that's pretty far away from this 1950, so I would guess that this model wouldn't hold up that long, but that's essentially what's happening here. We know that our a value can't actually be 0, but it's really, really tiny. And then this represents like a 2% growth. Okay, because remember that 1 just indicates that there is growth happening, so 2% growth, and then there's your power of x. So if I wanted to do, and this question didn't get asked here, but I could now use this model to come up with, what's the population going to be in 2020, and I could plug the year in here. I would just want to make sure that however I put my year in here, it's kind of consistent with how I typed my data in. By the way, this number might not have come out so scary if I had done something like put this in as 50 and 72 and 84 and so on. So that's another tip you can use if your numbers are coming out gross. Okay, let's do some modeling. Well, this is another type of modeling with data, but the data is just given to you in a different way. So the population of a certain cell type was 100 on the 2nd day and 2,700 on the 5th day. Assume the growth is exponential. So first it says find the number of cells present initially, and then how many are expected on the 7th day. You might be able to work this out, okay, mentally. You may be able to come up with, all right, if we know that there's some multiplier that gets me from 100 to 2,700 in 3 days, can I come up with what that number is? But I think an easier way to do this, anytime I'm given data that's kind of paired together, so like these 2 things are put together and these 2 things are put together, I'm going to put these together almost like coordinates. Now, I do want to be careful about which one is my independent variable. In this case, the day would be my x, and the number of bacteria would be my y, because the number of, or sorry, not bacteria, but the number of cells would be dependent on what day it is. So I'm going to think of this as the coordinate 2, 100, and I'm going to think of this as the coordinate 5, 2,700. And then I'm going to do exactly what we just did in example 3, but only using these 2 data points. So stat, edit, clear all that junk that I just typed in. In my L1, I'm putting my numbers of days. In my L2, I'm putting 100 and 2,700. By the way, there is a algebraic way I could do this, and if we have time in class, I'll take the time and show you. I don't want to bog down the video with showing you that because doing it this way is perfectly fine. But There is an algebraic way I could set up equations and solve it almost like a system to come up with my model here. But so I've got my two numbers in there. I'm going to go to calculate, and I'm going to look for that exponential regression again. And here's the model I come up with. I come up with the model. Now notice this isn't actually the answer to my question, but 11.1 repeating times 3 to the power of x. So now let's think about how to actually use this. The number of cells present initially, that's really just asking me for my A value, right? My A value is a little bit weird here, but I would feel comfortable saying that A is about 11 cells. I'm not sure that the decimal really makes sense here, but mathematically it came out with a decimal value. So we'll run with it and say that our initial value would be about 11. And so that's what's happening here is we started with 11 cells and we're tripling every day. That's what this model is showing me. So if I want the 7th day, I'm going to plug in a 7 for x. So I'm doing, and I do want to kind of stick with that 11.1 repeating. I am going to have to round it kind of at some point, but I'm going to go 11.1 times 3 to the power of 7. And so in my calculator, I'm going to go 11 point, and I'm going to just put a bunch of ones in there to show that it's repeating, times 3 to the power of 7. And I end up with 24,300 cells. Okay, on to example 5. Okay, example 5 is a half-life problem, and half-life really tends to throw people off, but half-life is really just saying, when I say a substance has a half-life of 24 years, that means after 24 years, the amount of substance remaining will be cut in half. Okay, so the amount is being divided by 2 every 24 years. Okay, so before I get into answering these questions, let's just talk about how to write the equation for this. This is going to be an exponential function, and I'll just kind of write that exponential model formula off to the side here. So if I'm following that, A is how much I'm starting with initially. So in this situation, I'm starting with 80 grams. Now my B value is what's happening to that 80 grams. Anytime I'm dealing with half-life, my B value is going to be 1/2 or 0.5 because that's what I'm doing to my initial value is I'm cutting it in half. So if that's A and that's B, how do I deal with this 24 years? And that question tends to come up a lot in half-life problems. So here's the thing. If I just put an X up here, then what's happening is I'm taking this 80 and cutting it in half every single year. Every time I put a new number in there for X, I'm cutting in half one more time. But I don't want to cut in half every year. I want to slow this down. I want to group it into groups of 24. So the way I handle that, if I've got all these years kind of spread out in front of me, and I want to put them into groups of 24 to figure out how many times that I'm actually cutting in half, I'm going to take that X and divide it by 24. Oh, sorry, that's going to run off the page there. But so that's how I deal with the half-life, is I always divide by whatever the half-life is. So maybe on the bottom here, I'll write this down. Anytime you're writing an equation for half-life, it's going to look like this. Y equals the initial value, which we know is A, times your B value of 0.5. And then up in the exponent, instead of just having an X, you're going to have X divided by whatever the half-life is. Every single half-life problem is going to take on that form. Okay, so if you can kind of wrap your heads around that, hopefully that will help. So this first question I threw in here, so you could do it without even working with this function. I probably could have gone ahead and answered this one without writing that equation out. Because 24 divides evenly into 96, right? 96 or 24 times, let's see, blanking for a second, 24 times 4 is 96. So this 96 years represents 4 half-life periods. In other words, we're going to cut in half 4 times, okay? So if I was kind of working through this mentally, I would start with 80, and then I would cut in half once and go to 40, and then I would cut in half again and go to 20, Then I would cut in half again and go to 10, and then I would cut in half again and go to 5. So here's 24 years, here's 48 years, here's 72 years, and here's 96 years. Okay? So 5 grams would be remaining. Now, I did that without actually using the equation, but I'll show you in a second that you could use the equation to answer that question as well. It gets a little harder when I give you a number that's not a perfect multiple of 24. Now, this is close, right? We could estimate it because if I do 24 years twice, that would give me 48 years. So we just said here, this would be 24 years, this would be 48 years. So we're guessing it's going to be a little less than 20, but if I want the actual number, I'm going to have to use this equation, okay? So in my equation, I would say 80 times 0.5, and then I'm going to take that 50 and divide it by 24. And what that's really doing is telling me how many times am I cutting in half. So in my calculator, I'm going to go 80, whoops, calculator just turned off, 80 times 0.5 to the power of, and in my calculator, I'm going to need to use parentheses here to do the 50 divided by 24. Depending on your calculator, you might be okay without it. And remember, I estimated it to be a little less than 20, so I feel good about 18.88, I think is what it was. Let's just check our answer to this first one using that equation, okay? If I had done the same thing, so I'm going to bring up that same equation, but if I had put 96 years in here instead, in fact, it does give me that 5 grams that I came up with this way. Okay, so just wanted to show you that you could have used the equation on that first question as well. Okay, oh, this is a dumb question. I didn't realize that was like that. When will only 5 grams remain? Well, we already came up with that, didn't we? That was this one, okay, in 96 years. I didn't catch that. So a question like this one, and I think this was the reason I put this on here, not realizing that I would have answered it up above. Really, your best bet right now is to just take this 80 and start cutting it in half and hoping that it lands somewhere close to this 5. And in the case of this question, it's going to land on there exactly, right? Because when I cut in half, I'm going to land exactly on the 5. Really, what this is asking you to do is put this 5 over here for y and then solve for that x. Right now, you don't have the tools available to you to solve for that x. I'm lying. You do have the tools because you learned them in Algebra 1, but I haven't taught them to you yet this year. So we're not going to worry about ever having to actually solve for that x right now until later this year when I show it to you. Right now, if I ask you a question like this, it's either going to have to be an estimate where you can just get really close to it, or it's going to be something where you can just take that initial number and start cutting it in half and see how many times it takes you. But if I hadn't done this question up above, probably what I would have done is taken that 80 and multiplied by 0.5 and said, okay, so there's one round, right? That's one half-life period. And then multiply by 0.5 again. There's 2 half-life periods. Oh, I did not multiply by 0.5. Let's see. There's 2 half-life periods. Now I'm going to multiply by 0.5 again. There's 3 half-life periods, 4 half-life periods to get to 5. So 4 half-life periods, if every half-life period is 24 years, is 96 years. Okay? Okay, so I think that was it for this lesson. Yep, just checking. Just some different versions of exponential modeling, but you will want to know exponential regression in your calculator, and you will want to know how to do half-life problems like this one down here. Okay? All right, go ahead and get started on homework.